Alright, so now we're going to move to problem number 684, which is redundant connection, and it's marked as a medium level problem. So in this problem, a tree is an undirected graph that is connected and has no cycles. You are given a graph that started as a tree with n nodes labeled from 1 to n with one additional edge added. The added edge has two different vertices chosen from 1 to n and was not an edge that already existed. The graph is represented as an array edges of length n, where edges of I is ai comma bi, indicates that there's an edge between nodes ai and bi in the graph. Okay, now we need to return an edge that can be removed so that the resulting graph is a tree of n nodes. If there are multiple answers, return the answer that occurs last in the input. Okay, so let us see what this example says. So we have edges 1, 2, then 2 to 3 and 1 to 3, right? So redundant connection would be 2 to 3. That is, if we remove this edge, our graph would still be connected, all the nodes would be connected. And what is given is that resulting graph is a tree of n nodes, right? And you're given a graph stated this: the added edge has two different vertices chosen from 1 to n and was not an edge that already existed, right? So basically what we need to do is convert this graph into a tree. That is, we have to remove the redundant edge in order to form a tree. So this is the resulting tree: 1, 3 and 2, right? Now you might say that we can also remove this edge, right? So yeah, you can definitely do that: 1, 2 and 3. This would be resulting graph then. But this says that we need to return the edge that can be removed so that resulting graph is a tree, given that in case of multiple answers, we return the answer that occurs last in the input. So the edge that has been added last in the input, that needs to be removed in order for us to reach the tree. Since this edge 1 to 3 was there earlier, like before the last input, we don't take this. Instead, we remove this edge. That is the last one. So the last occurring input, the last answer, basically the last edge would be removed. So that is the example 1. Now moving on to example 2. You see here also we have this, and this is the graph that has been formed. 1, 5 is the last edge, but if you remove the last edge, considering this as the redundant edge, then you see that 2, 1, 3, 4, right? This is the graph that is being formed, and 5 becomes disconnected. So now this is not a valid tree because we have disconnected one node from the whole graph. So this cannot be removed. Now let us check if we can remove 1 comma 4, that is coming last in the input before 1 comma 5. So if we remove this, definitely 2, 1, 5, 3, 4, this becomes a valid tree, right? So yeah, we remove 1 comma 4. That is the redundant connection, we return it. So that is about this problem. So now let us get to the solution. So our approach is simple. We add edges one by one, like we have to form the graph, right? The graph is not already formed. It has been given in the edges vector type. So we have to form the adjacency list in such a way that when we are adding, we check whether adding the current edge creates a cycle or not. So we start with an empty graph for each edge u comma v. If both u and v are already connected, in the graph, that means there is already a path from u to v. Then adding the u to v edge creates a cycle. So basically u to v are already connected by some other path, right? Which we have checked that they are already connected. Then adding a uv, then adding a new edge would create a cycle. So this is our answer: u to v. This is the redundant edge that we don't need to add, or we basically need to remove if you think in the reverse fashion. Otherwise, add the edge to the adjacency list and continue. We use DFS to check connectivity between u and v. Now algorithm steps. So basically, we create adjacency list, iterate over each edge u comma v, create a visited array viz. If u and v are already connected, that is the DFS of u comma v returns true, then uv is a redundant edge. Else add uv to the adjacency list and return the redundant edge. Now the DFS function is basically, it checks whether v is reachable from u, right? So we mark each visited node to avoid cycles, and if u is equal to v, return true. Explore all neighbors of u recursively, because we are performing depth first search. And the time complexity for each edge, we perform a DFS that is, in the worst case, explores all nodes. So e of e times v, that is O of n square, since the graph is n nodes and n edges. And space complexity for the adjacency list and recursion stack over v plus e. Now let us get to the code, right? So basically what we are doing here is find redundant connection, right? So it takes the edges vector of int type, and n is the size of the graph, that is the edges size. We declare our adjacency list, an ordered map, int comma vector of int type, that would be storing the node u and the nodes that we can go to from node u, v1, v2, v3. So this is the format. Similarly, there would be a node w which goes to l1, l2, right, l3. So this is the format that we'll be storing our adjacency list. Now we go over each node right? And u and v is edges of I of 0 and edges of I of 1. So from u to v, we check if adding this edge u to v creates a cycle. If both u and v already exist in adjacency list and a path from u to v exists through some other path, then adding this edge would close the cycle. That means it would form a cycle, right? So if both u and v exist and are connected, this edge is redundant, so we return this edge. Basically, u and v is edges of I, so we return that, right? So the condition here is if adjacency dot find u not equal to adjacency dot end, which means that in the map, if we are able to find u, if there's u that we are able to find, and we are also able to find v somewhere else, right? And the DFS also returns true. That means they already have a path from, there's already a path existing from u to v. That means that in case we add this edge in the graph again, then it would close the cycle, right? It would create a cycle. That means this is the redundant edge that we need to return, so we return that edge, right? And else we add the edge to the graph. That means there was no cycle detected. There's no path existing from u to v right now, so we add them to the adjacency list. Both of them we add because this is an undirected graph, and we return this. Basically, we won't reach here as the problem guarantees a redundant edge would be coming. So in case no redundant edge was coming out, we would return an empty array, but that is not the case since the problem says there would be a redundant edge. Now let us get to the DFS function. So bool DFS, this is to check if v is reachable from u. So we pass in the adjacency list, the u and v edges, nodes, and the visited vector of bool type, right? So we first mark our node u, that is the starting node, visit of u is equal to true. Mark current node as visited to avoid revisiting. Now we check if u is equal to v, we return true. That means if we have reached v starting from u, then there must exist a path, right? And then this would be considered as the redundant edge. Now, if this condition does not hold true, we go over all the neighbors of u by traversing through the adjacency list. If the neighbor is not in visited, we perform DFS for it. So if visited of neighbor, we continue. Otherwise, if not, we perform DFS. If v is reachable, if v, the node v is reachable through this neighbor, that is, there's a neighbor, and we have, let us say, we have other neighbors too, neighbor 2, and then there's a u. So this we check if the DFS from u or from neighbor, since we are doing recursively, right? DFS of u would get to DFS of neighbor 2 and DFS of neighbor 1, right? Which would eventually check if v is reachable from that neighbor. So if this is becoming true, that means u would eventually be able to reach at v, then we return true. That means there is a path existing from u to v. Otherwise, we return false if we are not able to find any path from u to v. So that is about the function, and that is about the solution.